Our topic of study in this section would be uniformly accelerated motion in a straight line. So we are in kinematics right now. And what we will do, we'll spend the next couple of minutes to understand how we can apply the learnings of slope to decode or infer information from the various graphs that we come across in this topic. So since this is a little bit of physics, okay, let us also clear the air around this topic called uniformly accelerated motion in a straight line. In a couple of books, this is only written as motion or motion in one dimension. But if you just go through the words, you'll get all the information needed. So let's first see, it's uniformly accelerated. That means the motion has an acceleration. Let me denote it by A, and since it is uniform, I can write that the acceleration is constant. So the first thing that I get from here is that there is one player which is known as acceleration. Now since there is acceleration, you should have the velocity is changing, right? The velocity is changing with respect to time. So the velocity is changing with respect to time. So pick the word velocity is changing. That means you should have two identities for velocity. One should be initial velocity and the next should be final velocity, right? Final velocity. Let me denote them. This we denote by U and this with V. Okay, so we get two more parameters from here, one being U and another one being V, and with respect to time, so time is another parameter that we study in this particular topic. Now there is another word which is out here called straight line. So if you observe straight line, that means we are moving in a straight line. So this gives birth to the parameter displacement, which is denoted by S. So now let's pick up the words that we have got from this definition of this chapter, which is uniformly accelerated motion. You have a S, you have a U, you have a V, you have a and you have a T. So many books write that apply the Suvat equation. So if you have a motion which is a uniformly accelerated motion in a straight line, you can apply all the Suvat equations of motion. And what are the Suvat equations of motion? We have three equations. Velocity, final velocity is equal to U plus AT. That's how children memorize it. V equal to U plus AT. S equal to UT plus half AT square. And the third one being V square equals U square plus 2AS. So these three equations, don't just randomly go and apply them. Always read the scenario. If the scenario is of uniform acceleration and the motion is in a straight line, yes, Suvat is the equation you can apply. Now our topic of discussion won't be this will cover in another topic of physics when we'll be studying kinematics. Our topic of discussion here would be the graphs, okay, the graphs that we usually encounter with whenever the scenario is of Suvat equation. So let's see what type of graphs do we encounter. There would be three different type of graphs that are very common. The first one would be a S versus a T graph. S stands for displacement and T stands for time. S versus T graph. Okay, let's analyze the S versus T graph first. So something like this, and on the y-axis we have S, and on the x-axis we have T, right? This is the x-axis, this is 0, and say this is the y-axis. Let's take a plot out here, a straight line plot of this order, right? And let's now apply again the understanding of slope out here. Okay, so whenever we talk about slope, it's a straight line, so the slope is constant everywhere. Let's take 2 points and let's try to find out what does the slope of this graph infer to us or tell us about. Okay, so the slope is usually, by now we are pretty familiar with it, the slope is rise over run. Okay, the slope is given by rise over run, and a rise means always a difference. If you look at rise, the rise talks about difference on the y coordinate. Okay, difference on the y coordinate. So can I just tell it for my understanding purpose, y coordinate difference, okay, a y coordinate difference over the run, which is a x coordinate difference, right? Difference means difference of values on the x coordinate. So if you look at the x coordinate, this, sorry, let me pick it up from here. Give me a minute. Clean this up. So there you go. And typically name this as x1, this becomes y1, this is y2, this is x2. So all you're trying to do is a y2 minus y1 over an x2 minus x1, right? Or even if you do a many children get confused, even if you do a y1 minus y2 over, even if you do a y1 minus y2 over an x1 minus x2, it doesn't make any difference. So this is slope, okay, this is slope, the rise over run. So we sometimes get confused, what does the slope of an ST graph tell me? So all we will do here is we have to use a little bit of our common sense, and S is measured in meters and time is measured in seconds, okay? Displacement, the SI unit is in meters, time is in seconds. So what are you exactly doing? Now just replace the numerator and denominator by the units of their quantities. So Aukash, will I not write something like meters over second? Now look at meters of second, okay? Let us look at this term meters over second and ask ourselves, okay? Let's ask ourselves, is this familiar to me? Is this unit familiar to me? I say yes, this is familiar. And what is this? I said this is nothing but velocity. Velocity is always measured as meter per second. That's how easily you can decode. So once you see the graph, you just look at what is on the y-axis and what is on the x-axis and try to find out the slope. So slope is always y data over x data. Now find out the numerical data and then just plug in their units. I believe the second graph would become much more easier for you if you apply the same technique now. Let's take the second graph, okay? The second graph talks about V versus T. So we would have V on this side, T on this side. T is measured in seconds, V is measured in meters per second, and this is why V stands for velocity, so, and T stands for time. So let me take a small plot out here. Say suppose this is the plot, and let's try and find what is the slope out here. Okay, this is the slope. So we would say the slope for a VT graph, the slope of the VT graph tells me rise over run. So ultimately if we plug the units, it's a meter per second over a second. That makes it meter per second. That means it's divided by second. So you can write meters per second into 1 over second, it becomes meters per second square, or you can write it as meters second minus 2. And then the big question comes is, circle this, okay, bring yourself in your mind, have a big smile and ask, is this familiar to me? Is this familiar? I said yes, this is familiar. This is acceleration. Acceleration has got the units of meter per second square. So the slope of a VT graph gives me a quantity which is known as acceleration. Now let's look at the third type of graph, okay? The third type of graph, and the third graph, this was my second. Let's take the third graph. The third graph is an AT graph, okay? So A is in meter per second square, that's acceleration. So we call it A versus T graph, and this is in seconds, okay? So let's have a plot like this, and now ask ourselves, slope is equal to rise over run, okay, rise over run, and then I plug what I call as my units out here. So I get a meter upon second square divided by second, so I get a meter per second cube. And I ask myself at the very preliminary stage where I am right now studying kinematics, that is this familiar to me? I ask, is this familiar to me? My answer would be surprisingly no, this is not familiar, okay? So slope of a AT graph, it does not give any information about, okay, slope of an AT graph does not give any information about any parameter of, SUVAT. In higher classes, you will study that this tells you about rate of change of acceleration, which is known as jerk. But right now, at motion in one dimension, we would say the slope doesn't give us any sort of a conclusive inference about any data that we encounter on SUVAT. So let me make a small matrix out here and see whether we have understood what we tried to discover out here. So this is my small matrix, and we have three types of graphs out here. So this is graph number 1, row for 1, row for 2, and let's see. Okay, so let me write the graph type, and let me write what does the slope tell us all about, and what would be our remarks. Okay, so the first one would be the S versus T. So the slope will give you usually a meter upon seconds. That means it talks about velocity. The second one would be V versus T. So the slope would be meter per second over second, which is meter over second square. So it talks about acceleration. And if we see the third graph, that is A versus T, the slope is meter per second square over second, which is meter per second cube. We'll say this is inconclusive. Inconclusive from our understanding. And if you want, you can write the units also out here. This is meters, this is second, this is meter per second over second, this is meter per second square over second. So see how easy it becomes. Hope that makes your understanding clear. Whenever you come across motion in one dimension and encounter graphs, what does the slope tell you? Look at slope. Slope means y data over x data. So look what is the y data, find out what is the change in y data over change in x data. Once you solve the numeric part, plug in the units out there, the SI units, and the SI units itself will tell you what type of quantity the slope is inferring. Hope this is useful and helpful for you from now on to decode graphs that you encounter under motion in one dimension.